Hey, how's it going, y'all? I guess I want to make maybe two more videos, this one and one more after this, just for your viewing pleasure. I'm just kidding, this physics stuff. For right now, for this video, I just wanted to go over some problems that we covered on the first half of the year, mainly dynamics and stuff like that. So, I grabbed these problems from your previous tests. Um, so hopefully they're familiar and or they remind you of how to do these problems. And of course, when I give you these short answer problems, they're quite difficult. So hopefully I can go over them. And again, it can reinvigorate your mind and your thinking. I know times are tough now, again, because you're doing your test, but hopefully one test per day is not too stressful. And again, I hope you try your best. All right, so right here we have this skydiving adventure. Oh, that's me, and I have this terminal velocity. So again, in free fall, something will fall and it'll keep going, it'll keep accelerating, and the speed will continue to increase. But when I have terminal speed, that means it stops right there. This is the speed, this is the maximum speed that I can obtain, okay, as I approach the ground. So during an attempt to snap one last photo with my camera, I fumbled it from a height of 52.1 meters above the ground. Okay, determine the speed at which the camera hits the ground. Okay, so here's the thing. I guess I did add a few things to this problem, maybe too much, but let me explain my thinking here. So because I had the parachute stopped me, but my camera kept free falling to the ground. So I think I mentioned free fall right here. So now let's do this. Okay, so determine the speed at which the camera hits the ground. So look, we need to identify a couple of things. Well, if it's me, I assume I'm here on the earth. So that tells me that, let's write down our node. So, not that. Okay, so I'm using paint. It's a little different, but hey, let's try to see. So G, oh, you know what? Let me use a different one. Let me use something a little thicker. Here, let's use that. So G equals 9.8 meters per second squared. If you thought my handwriting was bad on the board, oh boy, you're in for something here. Now again, so since it's on Earth, that's what it should be. Let's write down, I think my initial velocity was 10.4. I can change that if I need to. And that's meters per second. And then, so again, that's my initial velocity. Let me rewrite that part right. So V naught, or you could put a VI, that's okay. And then my height, I want to say was 52.1. So let's write down our knowns, okay? 52.1 meters, okay? And we're trying to find our unknown, and that was the velocity at which it hits the ground. So let me just change the color. Do you need to do this? No, but that's what I'm trying to find. Okay, so that's the kind of interesting thing, right? What kind of problem can I, how do I solve this problem? And of course, like most problems, you have to write down where you're trying to go, what you have, and what you have at your disposal to get there. So I wrote down my knowns, my unknown, and I need to figure out what equation matches this. And if you look at your equations, all the ones that I've given you, I know there are many, but you should find that there's this one equation that is written like this: v squared equals v naught squared plus 2a and then delta x. Now, is there an h in there? So here's the thing. To be able to figure out what equation you need to have or which one to use, you need to figure out what is in there and what is not. One thing that's kind of important to notice is that there is no time in here. So if there's no time here, then right now I can't use time to figure out my final velocity, which is very common, right? There's a very easy equation that has time in there, but since I don't have it, I have to use a different one, and it's this one right here. And again, notice that it's going to fall 52.1 meters, and that would be our displacement. Okay, so again, you have to understand that h and delta x this time are the same thing. You have to be able to understand how you can manipulate that, those ideas into that. So right here, and I'm trying to find the final velocity. So it's not too bad. We already have it right here. We just need to get rid of that. Okay, so to get rid of that, I need to do v equals, and then the square root. The square root of all this madness. V naught squared plus 2a. And then I'll just write x instead of delta x. Just it's the same thing right now. I'm trying to write less as possible, the least amount as possible. So this is what I'm trying to find. I'm trying to find v. Okay, so I'll bring this over here. Okay, so v equals the square root, and then we'll write v naught in there. So v naught is 10.4. Meters per second. I think I might not write the units for the next few problems. That's okay. Plus 2 times parentheses 9.8 meters per second squared, and then times 52.1. You know what? I should have written my answers down before I did this problem. So let's see that. And the reasonable answer seems to be 33.6 meters per second. I think that seems about right. So this would be our answer for part A. So determine the speed at which the camera hits the ground. Good. Forget about the sig figs. We're not doing that right now. I was very picky about that initially, but honestly, once you start getting into later physics, sig figs are important, but not in this way that we think about them. So determine the time it takes for the camera to free fall from, right, that should be me. Senor Martins. I don't have the Enya there, but that's okay. Hands to the ground. Okay, so what's the time it takes? Well, okay, so let's give ourselves some room here. Okay, so let's write it right here. I'm trying to find the time. And there are multiple ways to do this. Let me just do it the easiest way so that I don't have to write as much. So right now I have my acceleration or my gravity. It is the same. Now, if I am writing this using this program, and it's, it's not easy, boys and girls, then you should know also that you should be writing this in your papers as well. Yeah, there we go. There we go. Okay, so write this down, please, when you do this test, and with all problems, math, physics, chemistry, anything, write it out, please. Okay, so then we have the initial velocity, 10.4 meters per second. Okay, and again, remember when you do these problems, whatever you get your answer for part A, I will not mark you wrong if you do it correctly for part B. So if for some reason you put 100 or some other reason or some other problem or some other number, I mean, if you did this process correct for part B, yeah, I would still give you full credit, but just because it's about the process more than anything, right? Okay, so if I have time, and I also have the displacement, but I don't need that right now. Look, I have acceleration, initial velocity, final velocity, and time. I wonder what equation can fit that. Okay, remember, v equals v naught plus the acceleration times the time. I know my time and the plus sign are very similar, but this is how it goes. Okay, this is what it is. So in order to get my time, I just need to manipulate this. Okay, minus the v naught and then divide the a. So t is going to equal to v minus v naught, and then both of them divided by the acceleration, which is going to be equal to v is 33.6. Yeah, I'm not going to write meters per second. You know it's there. Times 10.4. I mean, you should write it in the test, but oh, now Mr. Mars being a hypocrite. 9.8. Okay, so this should be a little bit above 20 divided essentially by 10, so it should be a little bit over 2 seconds. Let me give you a good answer, however. 2.37. Okay, so that's the speed at which it would hit the ground, and this is the time that it would take for the camera to hit the ground if I lost it from my hands at 52 meters above the ground. Okay, hopefully that makes sense. Is there a way I can erase this? Don't save. Bye. Okay, so now this is a momentum problem. Okay, so we have a student on her Harley, and they are both going this speed in this direction. So again, we have to combine both of these because we have the student on this Harley at 12 meters per second. She has a head-on collision. So again, they're going in opposite directions. Okay, so you have to notice that. Okay, if two things are going in the opposite direction, that means that their velocities are going to have different signs. Okay, that means one of them is going to be positive, the other one's going to be negative. Does it matter which is which? Not exactly, unless I specify one direction is negative or positive. It doesn't matter. You can choose your direction and the rest will fall. Okay, but since we have a Harley and a person in a Harley, and we have a little baby pigeon, I'm probably going to make this the positive side and this the negative side. So there's a secret negative sign right here that I don't tell you about, because you should know they're going in opposite directions. One of them is going to be negative. So how fast is the motorcycle going if the bird lands on the motorcycle after the collision? It's funny, during the test I've had some students come up to me or ask me, is the girl still on the bike? Like it'd be, I can understand why I should have written the motorcycle and the girl going, but yeah, that would be kind of a really sad problem if I had that poor girl fall off the bike. Yeah, I'm mean, but I'm not that mean. Okay. All right. So 59, 220. Okay. So let's see. The mass one is going to be equal to 59 kilograms plus 220. Okay. That should be 279. 279 kilograms. Okay, and then the initial velocity is 12. Oh man, apologies. 12 meters per second. Okay, again, don't worry about sig figs here. And then the bird is 2.1 kilograms. And then the velocity, I think, is negative 44. Let's check one time. Negative 44, correct. So this would be, I'm going to do negative, and then 44 meters per second. Okay, so now these are my knowns, and we're trying to find essentially the velocity of all of them. Okay, again, the girl's still on the bike. So, I guess you can't see that. Nice. Okay, so here, when it comes to momentum, okay, even with explosions, elastic or inelastic, look, it doesn't matter. This is the main idea behind all of them, okay? The sum, that's sigma right here, the sum of the initial momenta is equal to the sum of the final one. That ugly E is called sigma, right? So the initial momentum is equal to the final one, okay? And the thing is, you could memorize the inelastic and the elastic and the explosion stuff, but this is the main idea right here, okay? The beginning is equal to the end. It's conserved. Unless there is some impulse, and then that changes it. But there's no impulse here. Yeah, it's just momentum conserved, okay? So, assuming they stick together, that means it's inelastic. So, let's write our own version of this equation. So, look, I have this momentum of the girl on the bike and then the bird. So this would be M1. Remember, okay, just for those of you that may have forgotten, P, separate equation, P is equal to MV. Okay, so this is review. So hopefully we remember that. That's really important. So M1, V1, so the first momentum plus the second momentum is equal to all the momenta combined, okay? Because they stick together. The bird stays in the motorcycle. So that would be M1 plus M2 times, we'll call this just the final velocity. Okay, another way to imagine that is just to do, look, the first momentum plus the second momentum. So this is of the bird, this is of the girl on the bike, and this is going to be all their momentum. I'll just call it PF because there's only one. If they're all combined, there's only one. So it'd be M times V, but we have to combine, we have to add the masses. Okay, so the question was how fast. Okay, so if I ask fast, you can change that to speed. So I don't need the negative sign or positive sign. So if you were to make this negative, again, you could make this negative, this is fine. Or if you really want, you could make this negative and this positive. I would just want the speed, okay? So you could find the velocity, and then if it's negative, just change it to positive, okay? So, you know, either way would be fine. So again, so we're trying to find this part because we know this, and we know what these two are. So we have to find that. So some of you like to plug it in first. I like to solve for it algebraically and then just plug it in after. Okay, so VF, okay, I move this over here, and then I divide both sides by this right here. Do you see that? This goes to both sides. Divided by both sides, it's gone here, and then it's over there. So VF is going to equal to M1 V1 plus M2 V2 divided by M1 plus M2. Okay, so now we plug it in. Okay, M1, I'm just going to write 279. I'm going to change the color for the velocity. Why not? Times 12 plus the mass would be 2.1, and then here, let me put a parentheses here, because you're going to see right now times this should be, ooh, that's an ugly parentheses, negative 44. Okay, again, I'm not writing the units, but this should be kilograms, and then meters per second, and this is negative if you can't tell. You know what, I'm gonna make it, I'm gonna do it red so you know that's negative. Now remember, in physics, negative is not necessarily a bad thing. It's a different direction, okay? Just like north and south, that's all it means, is that it's the opposite direction. So then divided by, and then we're gonna do the purple again, and then both of them. So 279 plus 2.1, that's 281 0.1 kilograms, right? That's just both of them combined. So what is that? Okay, let me get my not so trusted calculator. That should be 11.58. We'll just round it to 6. Why not? Meters per second. Okay. So it should be, it's a little bit less than 12. I mean, it makes sense. Even though the bird is going quite quickly, right? The bird is moving in that direction quite quickly. It's a very small bird. You're not going to change the momentum of the bike. Now, if it was a car, even less so. It would change the momentum slightly, but not as much. And the bigger and bigger something gets, again, you're not going to slow it down as much. Okay. Now, yeah, hopefully that makes sense. Control U, don't save. Boom. All right. Oh, this is going to be a hard one. All right. So maybe I'll try my best to draw it on here. If I hold on, come on. All right. Whoops. Okay, so we have a 10 kilogram block. Okay, so let me just try it. We have something. Oh, whoops. We have something that looks like this. It'll fall. And then that should be flat. Just pretend that's flat. And then this right here is really muddy. Really, really muddy. Okay. Now let's, the height here, what is that? 3 meters. 3 meters, 3.0. Okay. And to a 3 meter muddy flat section. So the distance from here to here is 3 meters as well. So it falls 3 meters, and we have a little box. We have a little box, little baby box, but it's kind of heavy. It's 10 kilograms. Okay. So I have a box up here. It falls down. Okay. My height one is 3 meters. My distance from here to here, and again, this could be extended more to the right. And the energy, the speed should not be lost until it hits the muddy section. So it's just, don't be confused that this is right next to this. So again, this is a quite challenging problem, but luckily I'm here. And we have a coefficient of friction, which is 0.20, okay? So the coefficient of friction, mu, is 0.20, okay? For this muddy section, which means it's going to slow down, right? If there's friction, it's going to slow down. Okay, so my question is, find the velocity of the block right before it hits the muddy area. Okay, so I want my velocity, where's a good color right here? All right, so I want my V right here. Okay, we can call this V1. And then we want V2 right here after the muddy section. Okay, find the velocity of the block after it passes through the muddy area. Okay, so this is two different ideas. Okay, so this first part, ignoring this muddy section, this is just conservation of energy, right? My potential energy falls down a little baby hill, and then it's going to pick up kinetic energy. That potential energy will be transferred. And so I need to convert this energy into pure kinetic energy right here at the very bottom, and then find the velocity. So that's not too hard, okay? So hopefully remember that. Now I could ask you for the velocity right here, which would be a little better because then the potential energy would be half used or half converted to kinetic. But from here to here, it's not too bad. So let's see. I know my energy, mechanical energy, but I'll just write E. So my E1 is going to equal my E2 because there is no muddy section, right, until I reach here. So this is going to be E1 right here, and this is going to be E2. I know that's V1, but you know what? I'll call it E0. E0, E1. There we go. There we go. So E0 equals E1. Cool? All right, and then this is going to be E2. But if there's a muddy section, we should know that E2 does not equal either E1 nor E2, or sorry, neither E1 nor E0. Get a big old red. Okay, go back to orange. So, do we see that? This energy would not equal that because energy is not going to serve through the muddiness because there's friction. There's work being done. It'll slow it down. But right here it is equal. So at E0, let's figure out. It's not moving, right? It's at the top. So then it means there's no spring there. So there's only gravitational potential, okay? And it's sitting on there. So there's no even kinetic energy. So that means that E0 is only going to be potential energy. So I'm just going to write mgh equals, and then this right here at the very bottom at V1, this point right here, right, where I'm asking about, there's not going to be any potential energy, right? No spring, no gravitational. It will all be kinetic. So I can just write 1/2 mv1 squared. Now, again, this is, look, if you know your kinematics, you could also just pretend that this fell from here to here and you could ignore the masses, right? But we've already done a little kinematics, so just know that you can do that if there is no work being done. But let's figure it out here, right? And then we'll solve for V2 later. So mgh, so this would be 10 kilograms up here times okay, I'll use 9.8. I want to use 10 just to be lazy, but it's okay. Because then that'd be nice and 300. So then this should equal, you know what? I will use 10 because the less I use my calculator, the better. Okay, so this would be 300. Not 360, 300. Okay, so that's 300 joules, and that equals my kinetic energy. Do you see that? So the energy up here is 300 joules, and that's going to equal the energy right here, which equals 1/2 mv squared. Okay, so we just then have to find v. Okay, so that means I multiply by 2, and then I divide by 10. Okay, so 600 divided by 10, 60. Do you see that? So then I'm going to have v squared equals the square root, I won't write it out, just write 2 times 300 divided by 10. Okay, so the square root of 60, that'd be something slightly less than 8. Let me give you a good answer right now. 7.75. Okay, so my initial velocity right here is 7.75. Okay, if you use 9.8, it would be a little bit lower than this, and that's okay. Again, I'm just trying to limit the work that I do because physicists, you know, they're just lazy, man. They really are. So now here's the thing. The energy here cannot equal here because we have this muddy section. Now, how do I combine work and energy together? That's the problem, okay? So if you know my corniness, you should remember that woke is good, but womi is better. But in this case, woke is actually perfect. And what I mean by that, no, I don't mean that cheesy stuff that people are into, okay? I mean work is equal to the change in kinetic energy, okay? And also work, you should know this from before, okay? This is something that I taught you later, right? But work is also equal to, I mean, there's the cosine theta. I'm going to ignore that right now. But it should equal to force times applied over a certain distance, okay? So we have work is the change in kinetic energy, and then force times a distance. So since A equals B and A equals C, then B equals C. So then we have this force times the distance equals the change in kinetic energy. Okay, Now you may be asking yourself, Mr. Martin, where's this force? Blah, blah, blah. Okay, I'm getting to that. Okay, guys, you're always so impatient. Okay, yeah, you in the back, stop talking. Hey, it feels just like class, right? Okay, so now we have to think what force is being applied. Okay, so if this is muddy and there's going to be some coefficient of friction, there's going to be a frictional force being applied uh, while this block is sliding through this muddy area. Okay, so it's going to slow it down. So that's actually the force of friction. Ta-da! But remember, what is the force of friction equal to? Man, another equation that you guys have to remember. Okay, force of friction is equal to mu times force normal. Okay, wow, that's crazy, right? And remember, force normal is perpendicular. Oh goodness, let's try that again. You know what? I'm going to use this. I'm gonna cheat. Perpendicular, nice. Okay, perpendicular to the surface. Okay, so since this surface is perfectly flat, then the force normal can just be the weight. Okay. I know, a lot to take in. Yeah, this is why that part is hard. Okay, this is why I give you part B. Okay, part A is one that we should be able to do. Okay, so this we should all be able to do. It's not the easiest of problems, but it's a good problem that we should be able to do because we've hammered that in since last year. This one, this part B is, this is me trying to separate, okay, who has a good grasp on this, who has a really, really good grasp on this, and who's fairly close or, who needs a little bit more help. So then I'm going to plug that in, okay? So then I have this. So this, instead of force of friction, it should be mu times, and then the force normal is just going to be mg times the distance. A lot of you did this part correct, but then you forgot the distance right here. And this equals change in kinetic energy. Ooh, let me write that. Change in kinetic energy. Remember, change in physics means final minus initial. Okay, so this is going to be final, or we can think of it as V2. Okay. Initial. So we can think of this as 1 and we can think of this as 2, E2 and E1 right here, okay? So let's figure out what this numerical value is, however, okay? Yeah, it's a lot of algebra. It's going to be tough doing this. Okay, so 0.2 times 10 kilograms, right? And then again, I use G10. Let's just keep it 10 right now. If you use 9.8, that's okay. That's better, in fact, but like I said, the less work I have to do, the better. So time, and then 3. My distance is 3. Okay, so that would be, I think, 60, right? So that would be 0.6 times 100. Yeah, that should be 60. Okay, so this would be 60 joules. Actually, that should be negative 60 joules, because again, friction takes away energy, so I should have added that negative sign for the force of friction. Okay, so that means that this is going to have less joules than here. Do you see that? So my kinetic energy, I'll call that E2 minus E1 is negative 60. So if I know that E1 is actually 300, so it's a good thing we did this method. E1 is 300 right here, then E2 has to be 60 less than that, which is 240. So if you do that, you just do plus E1 to both sides. So 300 minus 60 is going to be 240. So E2 is equal to 240 joules. Okay. Again, this is a challenging problem. I didn't ask you for the kinetic energy. I asked you for the velocity, which, so 240 equals 1/2 mv squared. Okay, so then, and then this is 2. So the velocity after the muddy part is going to be v2 equals, and then the square root of 2 times 240 divided by and then it just so happens that my mass and my acceleration are the same, so 10. Okay, so 480 divided by 10, and the square root of that, okay, that should be right below 7. Mr. Martin can't do math anymore. Let's just do this real quick. So it'd be really, really close to 7. 6.93, we'll call it. If you used 9.8 instead of 10, it would be a little different. So you can actually see it did slow down quite a bit, almost by 1 meter per second, which is roughly, approximately 2 miles per hour. So something that's kind of noticeable if you're going at that speed. So again, that is quite challenging. Now, will I give you something as challenging as this? Maybe not as challenging, but maybe not far. Not too different from that. And then we have this kind of problem, which again is quite challenging. Okay, let's do this. Man, I just like giving you guys a challenge, and plus, since it's open note, come on. Okay, so let me draw this. I have a dot here. We'll make these arrows. And then I have one, we'll make it a red one. Oh no, make that black. Okay, then we'll make a new one. We'll make a red one. Boop. Okay, so it should look something like this. Okay, so this is 2, 2, 5, and then 5. Okay, and then 37. So let me write silver. Oh no, not that anymore. 2, 2, 5, and then 5. Okay, just, oh, by the way, this is black and silver. Raider Nation. Raider Nation. Okay, and then this right here, we'll make this a little bit smaller. We'll make this, was it 37 degrees? I think it was. Oh, 37, okay? Jot it down, 37 for you, okay? And this is between this. So I need to split this thing up, this little force thing, and I don't even have the problem. I really don't care about it, but it's like 25 kilograms. Ooh, that's important. Let's write that down. Mass is 25 kilograms. Technically, you should actually put this right here. That's okay. Let me draw these arrows. Okay, these are vectors. Vectors are very important. If you do math or physics later on, they're very, very important, especially once you get to high-level physics. Oh, man. Oh, boy. All right, so starting from rest, use the acceleration to find. Okay, so the distance. Oh, man, this is a challenging problem. Again, I don't think I'll give you something this challenging, but it's good to know. Find the distance, okay? So I need to find the distance, but I need to find the acceleration first. And so I just told you to find the distance, I need the acceleration, and to get the acceleration, I need the force, and I have the mass. So before we even try to find the distance, and this is my time, let's find the force, okay? So this is going to be challenging. Okay, so just look. Let's see if we can get, we'll add them all up together. Look. This is going straight up, this is going straight down, that's going straight left, and this guy's going at an angle. This is a little interesting, an eclectic fella, or an eclectic lady, and we need to actually forcibly change this little person to fit our needs, okay? Yeah, it sounds kind of sadistic, and physics is that way sometimes, you know, okay? So I need to actually convert this into the up or north direction, and this into the east, okay, or the right direction. So I need to do that, and then the trick here is knowing that this is 90 degrees. Okay, again, not the prettiest thing, but this is a triangle, okay? And I split this hypotenuse into its different legs, okay? So let's do that, okay? If you know a different way of doing that, of course, you're free to do whatever method you want. I am used to the SOHCAHTOA method, so let's just do this one. So the SOHCAHTOA, so sine, opposite. So opposite over hypotenuse, adjacent over hypotenuse, and then opposite over adjacent, okay? Now, to be able to figure this one out, okay, look at the angle. 37 is what? Is it right next to it? Is it adjacent? No, it's opposite. So for this blue part, oh, it just so happens. Wait, let me do that. It just so happens for this blue part. Did I use that one? I think so. We need to find that. Okay, so this, okay, we'll call it y. And we'll call this x. Okay, so for y, fy, I need to find fy from this, okay? So I know that, forget about that. Just know that's fy. That my sine of 37 degrees, make sure you're in degrees and not radians, this will change a lot of important things, is going to be equal to the opposite, which is my fy over my hypotenuse, which is, I'm just going to write 5 newtons because you already know what it is. You know what it is, okay? So in order to get my fy is going to be equal to, multiply 5 to both sides, so 5 newtons times sine of 37. Okay, 37 degrees. Okay, and that's, I'll do that in my calculator later. Voila, that's what it equal. I knew. Okay, now after we do that, we're not done, but let's do the x. Okay, so 37 is right next to it. It's adjacent, so we need to use cosine. Okay, we need to use cosine. So cosine of 37 degrees is equal to, it's equal to fx, the force on the x-axis, right, this part, over my hypotenuse, right, my h, which is 5. And look, it just so happens that the process is the same. Instead of sine, it's cosine, however. So fx is going to equal to 5 newtons times cosine of 37 degrees. Oh, that is so ugly. So fx is equal to some unknown, okay? Give me 1 second. So this should be 4, roughly. I'll call this 4 newtons, okay? And then this right here should be 3. Well, how about that? How about that? Okay, so this should be 4 and this should be 3. Okay, so I'm going to have to redraw this thing. I'm going to have to redraw this, okay? But it's not going to be as nice this time because I'm getting impatient. So look, I already have 2 going up. So look, I already have 2 going up, and then I'm going to add another one. Okay, so this is 2, and then this is going to be 3. And then this right here is 5. Oh, so ugly. This right here is going to be 2. Okay, so then this right here is going to be 4. Let's just make sure that I'm right. So that's 37 opposite. I'm pretty sure that's right. If it's wrong, oh man, it's going to be embarrassing. Okay, so look, let's combine all these. Look, you should know that it's 2 and 3 going up and 5 going down. So really, these cancel each other out. Voila. Goodbye. Funny how that worked out. And then if I have 2 going to the left and 4 going to the right, oh, look at that. Really, I can just change this now to, this is not a vector. This is me just showing that, look, now, in reality, it's just 2 newtons to the right. Do you see that? So if I had a vector, this much force going in that direction at that very specific angle, then what this object is going to do is move just to the right or the west. Do I have any? Yeah, just to the right. Do you see that? So all that craziness just translated to this thing just moving to the right at 2 newtons. Okay, so you can just say that. Okay, now I had to figure out the distance and the time. So I figured out my force. Okay, good. I found my force in the direction. Great. Okay, so my force is to, yeah, this is my, I guess my second time doing it because I helped you guys, but yeah, so F is equal to 2 newtons. Okay, now I need to find the acceleration because I said, well, one, I need to find the distance, but in order to find the distance, I need to find the acceleration. Remember, even non-scientific people know this, F equals ma. Okay, and my mass is 25 kilograms. So my acceleration is going to be 2 divided by 25. 2 newtons divided by 25 kilograms. Okay, off the top of my head, I think this is 0.08 meters per second squared. Okay, good. So we found the acceleration. And what is the distance the object will travel after 1 second? Man, I am not giving you guys any breaks, am I? So the time, remember the time is 1 second. Okay, now what equation can give me distance with acceleration and time? Okay, is this standing still? Starting at rest. Oh, perfect, man, not too bad. Okay, so again, looking at your equations, you should see, here, box that off. You should see that there is such a thing, delta x is going to be equal to 1/2 at squared. So again, I had acceleration, I had time, and I'm trying to find the displacement, but plus v naught t, which is just the initial velocity. And since it's at rest, rest means the initial velocity is 0, so that's a gonzo, zero, goodbye. Okay, so, oh look, and you know what? I wasn't that mean because the equation's already set up for it. You don't have to manipulate anything, you just have to plug that in. Okay, so I'm trying to find the distance that it covers. So in this case, it'd be the displacement, but if the initial position is 0, then the distance and the displacement are the same. Okay, not every time, but in this situation, yes. Okay, so then we'll have 1/2 times 0.08 meters per second, then times squared times 1 second, and then squared. Okay, so second squareds cancel out. So my delta x is going to equal to 1 squared, which is 1, 1/2 stays the same. Okay, so this should be 0.04 meters. Oh, can't control. Oh yeah, I can just do that. Look, done, done, done. So that is my displacement after 1 second if it's going in that direction. So hopefully this clears things up. I hope this helps everybody.